Hi, welcome to StatStuff. I'm Matt Hansen. In this lesson, I'll just touch a little on the concept of Statistical Process Control, or SPC, and how it's used for measuring variation. This won't go too deep into SPC, but some of the concepts do build on the prior concepts about spread and variation, so you may want to watch those first. For now, let's begin by quickly reviewing the differences between common cause variation and special cause variation.
Well, in that prior lesson on the different types of variation, like common versus special cause variation, we described how not all variation is necessarily bad as long as we can control it and at least understand and try to control it. We talked about the differences between common versus special cause variation. We said that common cause variation, also noise, is something that we see that naturally occurs within the normal part of the process, and it usually reflects a normal distribution, and it's something that occurs within the process. It's typically something that's a part of the design or part of the normal environment where it is, or more maintenance, or those kinds of things that might occur on a common or more general natural type of basis for that type of process. But special cause variation, also known as signal or some sort of anomaly, is something that's not typical. It's something that's unnatural, erratic that occurs, and it often creates a distribution that looks non-normal. And it's going to generally be a primary source of pain for us in the process that we're trying to fix. And in this sense, it's also going to be coming from outside of our process. It's something that occurs outside, like a power surge or extreme weather conditions, or something that's not a part of the actual design that we had within the process itself. So in that way, we used an illustration before where we showed that there was a dartboard that had all these different darts. We said that common cause variation might be reflected in these darts that are on the far right-hand side, where they're generally close to each other, and being close to each other like this, they're not too far off. So these might be representing in this way some more consistent, yet still there's some distance between them, so there's general variation that might occur, or the common cause variation that might occur as far as how distant they are from one another. Whereas the other two darts that are on the far left-hand side, we might think of these as like the special cause variation. Something caused these to fall far to the left, something very distant from the other ones. And as a result, this might be something that's unnatural, erratic, that occurred in the process that caused it to fall away to a distance that's much further away from the other darts.
Okay, now let's begin to define what we mean by Statistical Process Control, or SPC.
Well, SPC is a method of measuring process data over time so that we can find and fix special cause variation. They're usually control charts that we would use in order to help find these types of special causes within the data or within the process itself. SPC also explores DOE, that is design of experiments, but we're actually not going to be getting into that in this lesson. DOE is generally something that's a very detailed method for designing tests or experiments for measuring the kind of variation, but this is not the type of thing that we're going to be looking at now. So why should we only find and fix special cause variation? Well, common cause variation, again, that occurs naturally and normally and randomly within a process, is going to be a lot harder for us to find and to fix. But special cause variation actually appears more inconsistent, and it's a lot less predictable. So in that way, when it stands out, it's a lot easier for us to detect and fix. So what if we identify the wrong type of variation? Well, if we identify the wrong variation, it could lead to a type 1 or type 2 type of risk that is analyzed later in hypothesis testing. So just as a brief introduction to that, it's usually going to be like the analyze phase within the DMAIC process and the DMAIC methodology when we explore those two different types of risks. The type 1 risk, which is also the alpha risk, is the chance of treating something as guilty when it's really innocent, or like we may say from a courtroom case, we're convicting the innocent. A type 2 type of risk, which is the beta risk, is the chance that we're treating something as innocent when it's really guilty. That is, it's like we're letting the guilty go free. So just as the form of an illustration here, if the actual type of variation is common cause, and yet we're misinterpreting it as special cause variation, then it could lead to a type 1 error, or an alpha risk, where instead what it could give us is a lot of wasted time. The problem really doesn't exist, but we're trying to fix something that really isn't broken. Now, we might have the reverse, again, if we misinterpret the special cause variation that might exist and we treat it as common cause variation. Well, that would create a type 2 risk, or type 2 error, which is a beta risk, and the outcome from that is the problem is not resolved. We're diverting attention away from where the true problem is, so we never end up resolving the true root cause, where the real problem is, and the condition will still exist.
Now we'll extend that concept a little further by seeing how variation can affect a process.
Well, as we explore how variation can affect a process, a primary question I might ask is, how can you tell the difference between what's good variation and bad variation? Well, any variation that occurs within the customer's requirements, again, the voice of the customer, whatever they're defining as good or bad, that's considered to be good or acceptable if it's falling within those requirements. And this will generally include common cause variation, and it should exclude any special cause variation that might occur. Now, variation that occurs outside of the customer's requirements, whether it's common cause or special cause, is going to be considered bad or unacceptable. So again, this may include common cause variation, but most often it's going to at a minimum include special cause variation. So just to look at an illustration of how we might lay this out, again, we have a normal distribution laid out here across this scale. And we might have within the normal distribution, we've got our median, and we also have some sort of variation or spread within here. Well, within here we also have defined the LSL, which is the lower spec limit as defined by the customer, as well as the upper spec limit as defined by the customer. So the customer is saying, we want the results to be somewhere between this lower level and this upper level. This is what the customer wants. And within this range, this is what we're calling the voice of the customer, the VOC. This is what's considered to be acceptable. So any variation that occurs within this area above the lower spec limit and below the upper spec limit, that's going to be considered acceptable. So that means anything that falls outside of those limits is going to be unacceptable. These are the defects. So if the actual distribution falls outside of there to some extreme, some far point out to the left as well as some far point off to the right, then anything falling outside of that range would be considered a defect. But that whole range itself and what we're actually performing, how the process is actually performing, that's what we call the voice of the process. That refers to its capability of what it's actually performing right now. So a portion of that is acceptable, but it does include some of these defects that again are falling outside of what the customer wants that we would say is unacceptable. Now, special cause variation we would say is always going to be bad. Common cause variation is only bad when it falls outside of what the customer wants, when it becomes a defect. So this is where common cause variation is not always going to be bad, because most often we're going to see some of that falling within this acceptable range of what the customer wants. Now, control charts are what we would use as a primary tool for trying to measure and find that type of bad variation, the special cause variation or whatever's falling outside the customer limits. So in that way, we would use control charts as our primary tool to try to look for that and hopefully see that from that point how we might fix it. And the control charts are actually be covered in a separate lesson. We go into a lot more detail on those.
All right, before we close this lesson, let's discuss how we can apply some of these concepts in a practical way.
We'll try to find at least 3 different metrics that your organization uses. Again, that would be continuous type of metrics, and they are metrics that tend to have a lot of volatility. And try to ask yourself some of these questions for each of those metrics. First of all, what kind of variation, like between common cause variation or special cause variation, tends to cause the most pain that your organization is feeling? So what kind of variation are you seeing within those metrics that's causing the most pain for the leadership in your organization? And has the organization ever misinterpreted that variation? That is, where they're treating common cause variation as if it were special cause or vice versa. Now, if they have done that, then what was the effect of that misinterpretation? And what do you think could be done next time to validate the type of cause and prevent any future type of misinterpretation, and hopefully avoid some of those similar mistakes before, as wasted time when you misinterpret common cause variation as special cause, or diverting attention away from where the real problem is when you interpret special cause variation as common cause variation.
Well, that wraps up this lesson. Check out StatStuff.com for many more resources that can help you achieve powerful results. I'm Matt Hansen. Thanks for watching.